Right, okay, so today we'll continue with type 1 turbines. We'll continue talking about basically the induction machine, right? How it's using the turbine system. And so a lot of this will be review of different powers that's in the induction machine, right? But as we'll see, it's good to keep the terminology straight. There's quite a number of different things that we're considering the generator. Okay, so it'd be good to have a review and look at what all those equations are and what are the different powers that we talked about in the machine. Okay. All right, so it's good. This is showing the setup, right? The overall setup of a machine. And the way we draw it is most times we'll draw the grid on the left. Okay, so this is we have the grid on the left. We have the generator on the right. Okay, so power flows from right to left. So that's just a convention of how these things are drawn. So again, we have a blades, the gearbox, the generator. There's a generator. This is some compensation capacitor we may have connect to the generator again to deal with some reactive power issues. Then we always need a transformer. Okay, for this kind of generators, the voltage you're generating at is actually quite low. So there's always a transformer afterwards to transform the voltage to be reasonably high. Then you connect this to the grid. Yeah, so that's the general setup of the turbine. Then if we look at the circuit diagram, right, our circuit diagram is something like this. So here, if you draw this, again, this is a grid. So VA1 is a grid voltage, some resistance, some reactance, some shunt reactance, X2, R2, R2 prime S1 minus S. VA2 over S. Okay. So we look at this, again, the system current normally is we want to compute current flowing this way, current flowing this way, right, to compute the power. So by convention, again, when you do the power computation will come out to be negative because the current is flowing into VA1, into the grid. Okay, so you have a negative active power. That just means power is going into the grid for this machine. Okay. So normally for this is some external source. Okay. So this VA2 prime is normally supported by some external source. You want to think about thinking, what if you attach a battery, right, to the rotor side of the machine? And the reason why you may want some external source is this source gets multiplied by 1 over S. 1 over S is actually a large number because S is small. Okay, so this source gets multiplied quite a bit. And normally what this source does is used to cancel out reactive power, used to supply reactive power to the system. So if the generator is not connected to an external source, then VA2 prime is 0. Okay, it doesn't, normally type 1 systems are not connected to some source. And then if you look at this, right, so if you look at this part, again, this is some negative resistor, right? This is just so if you have a negative resistor, sometimes we'll think of this as a voltage source. So sometimes it's sort of notationally more convenient to think of what the wind turbine is doing is actually providing some power through a voltage source. So sometimes you'll see this written as VD. This is just R times, this RD times IA2 prime. So this is just thinking, so this is negative resistor. We can either think of it as a, when current flows through it, right? The voltage increases when current flows through a negative resistor. So this becomes a voltage source. Right? So this is our setup. Again, what the blades are doing is the blades are basically generating this negative resistor. Okay, so that's where the power comes from. That's where the mechanical power goes. Right? The mechanical power generates this negative resistor, then that's get converted to electric power. So again, this is drawing out the type 1 system. Okay. So the main thing is to figure out power flow. Okay, so the main trick thing here is to figure out what are, where are the power going and what are the names for different parts of power flow. Because there's quite a number of places power goes. Right? The power first comes out of the gearbox. So this power comes out of the gearbox. This is how much power is entering into your generator. This is the amount of power we have. Okay. So this, after the power comes out of the gearbox, goes into your generator, what we have is we have some developed power. This PD is called developed power. Okay. So the generator has some efficiency, right? Not all mechanical power going into the generator will be turned into electric power. So the amount of power that gets turned into electric power at the right-hand side is called developed power. Okay. And our goal is to understand how does this thing, how do we get to this part? Right? How does the developed power relate to the output power? Okay, so that's what we want to know. Right? And so what happens to this developed power is goes through basically these two resistors. Right, so not all of the developed power gets to the output because we have R2 prime and R1. So you lose power in these two resistors. Okay. So here the power loss is, of course, this is called PCU2. Okay, the CU stands for copper loss, right? This is a heat being dissipated through the resistor. So we have some copper loss on R2 prime. So similarly, this power being lost on R1 is PCU1. This is the copper loss on resistor 1. And then there is another power that relates between both sides. This is called PG. So the power left over after you go through R2 prime, this is the amount of power called PG. This is the air gap power. This is air gap power. Right, so there are basically, if we talk about a induction generator, if we talk about a type 1 turbine, there's 1, 2, 3, 4, 5, 6 powers to track. Just from right, going from right to left. And the questions for this part of the class typically is find some of these powers. Okay, given some other values, find these powers. Okay. Any questions about this diagram or this setup? Okay, so this is very similar to how induction machine works. Again, it's writing everything backwards. Okay, so when you have an induction machine, when supplying a load, power flows from left to right. Here, power flows from right to left. Okay. All right, so if you look at all these things, right? So it's good to think about, when you're doing calculations, they're just what they are, they're equations. But when you look at this diagram, it's good to think about where can you squeeze sort of, right? If you want to build a better generator, right? How will you build a better generator? How will you build a better turbine? So number one thing is you want to make sure this gear, the P gear part, this is lost. right? This is, so you have a one gets multiplied by CP, the coefficient performance, then becomes P gear. PD is you have some losses through the generator, okay? Then you have two copper losses. So out of these two copper losses, which is bigger? Is PCU1 bigger or PCU2 bigger?
I think PCU2 is bigger because the current, the voltage is lower. That's mean the current will be higher in this area, right?
Okay, right. So the PCU2 is bigger, right? So that's correct. But can I make do you want to necessarily make PCU2 small? If you could make it small, would you want to make it small? No, right? You would not want to make it small because remember the negative resistor, that depends on R2 prime. Because this PCU2 depends on R2 prime. The amount of power you actually generate, PD, also depends on R2 prime. So you cannot make R2 prime 0. Okay, so let's be clear. If you make R2 prime 0, you generate no power. It's important to have some resistance on the right-hand side. Okay, so PCU2 is generally larger, and it's not something you can get rid of. Because to generate power, you need R2 prime to be not 0, right? Just to generate power. Okay? Otherwise, you have nothing on the right-hand side. Okay, so that's a little bit counterintuitive how an induction generator works. As you go ahead, yeah. You do want R2 to be not too small. You do want it to be not too small. Otherwise, you'll be very sensitive to the slip. Right? S changes a little bit. This will be very, very sensitive to the slip. Okay, so technically, this works with any non-zero R2. But in practice, you want R2 not to be very, very small. You want some R2 there to generate high enough voltage, basically. To generate enough voltage to have power flow. So R1, PU1 is in general smaller, and that's something you try to make it 0. Right? So you're going to try to make a resistor 0, make a better wire that's on the primary side, on the grid side. Right? So C copper 2 loss says typically you cannot make R2 prime 0 in this problem. Okay? So that's why air gap power is important. So normally the air gap power is not too different from the alpha power. So when we do problems, when we make the loss on R1 bigger, just because it's easier for the numbers to work out. And normally, so air gap power is an important number. So here it may seem a little bit, extra, right? So we have everything else, it's just one resistor subtract from the other. But air gap power in practice is important. That sort of determines how much power we can get to the grid. Okay. All right. Any questions about this picture?
About IM, do we normally consider it or we ignore it most of the time?
So IM in power calculations, right? The shunt, this shunt inductor, in active power calculations, it doesn't matter. There's no power loss in that branch anyways. What IM does, it will make your current calculation a bit more complicated. So normally we do not consider IM. So normally there's ways to get rid of IM actually. Right, you either do a 7A equivalent at the primary side, or we just completely ignore IM and not worry about it. Okay? So it's very rare we'll do a calculation actually explicitly with a shunt reactance in the middle. So of course nowadays, all this is done by computer, so this really doesn't matter how it's complicated or not. But for our problems, we typically get rid of IM in some way. Other questions? Okay, all right. So the goal next is to write out equation for all these things. Okay, so all these things are related to each other through some equations, through the slip, the current, and all that. So it'll be good to see where the equations come into play. All right, so this is our picture. All right, so let's think about the formulas and the equation that comes in here. So when we first comes in, right, we have this P gear. So that's the power we get from the gearbox. And this power gets lost in something called a rotational loss. Okay, so rotational loss means this is coming from the fact that the generator is something that turns and there'd be some friction, yeah, some losses. It's generally not a big loss. So P rotation is our loss. And the part that's are not lost, this is PD, this is developed power. Okay. And then this thing starts to branch, right? So there's many ways we can write developed power. So this is an important equation to have. So developed power, if you just look at the circuit diagram, there's one way to write it is to think of the developed power comes from this VD, this voltage. So this we can write as 3 VD IA2 prime times the angle between them, right? So there's one way to write the equation. So if you think VD as some voltage source, IA2 is some current, they have some angle difference, theta, cosine theta, then this is the equation. This is not the only equation, and this may not be the equation you use a lot of times. So another way to think about it, this is minus 3RD. Okay, this is another equation for it, equivalent equation. Because this is PD is the negative resistance. So the minus sign is to make PD look positive. Okay, so how the minus sign does is to make PD look positive. Because if we want to talk about the power being generated being positive, then we need this is a sign convention. So there's minus sign there. Right? Because again, we have a resistor, right? RD is a pure resistor. So the active power flowing through it is just the magnitude of the current squares times the resistance. Okay. Right? So this is our one equation. This is another equation. So we can expand RD out. RT prime S 1 minus S I2 prime squared. Okay. This is just multiplying it out. There is another way to think about this power equation. Okay, so this is developed power, right? This is developed power. And sometimes it's useful to relate this to the torque being generated. Okay, so if you can think of the power after the gearbox, after rotation loss, there's basically some torque, right? There's some torque that's coming from the blade, and this is generating power. So we relate power to torque. Okay? So to relate power to torque, basically, power is torque times frequency, right? That's how fast it's going, how fast it's spinning times the torque. So here we'll take it, so we can define this as TD times omega 2. So what this does is this is the omega 2, this is the rotation speed, right, of the generator, right? So the synchronous frequency is 60 hertz. Omega 2 is something slightly faster than the synchronous frequency. TD is a developed torque. Okay, so there's just many ways to think about this developed power. Right? So you can think about, say, voltage source with some current coming out of it. You can think of say, negative resistor with some current going through it. You can think of this being generated by some torque spinning at some frequency. Okay, so just different ways to think about it. And all this equation won't matter. Okay, so next homework is basically all these equations, shove them around and see how to compute different things. Yeah, so just bunch of equations. Just remember, a lot of equations are about the same thing. Just different ways of looking at powers. All right, so this is the developed power. So after the developed power, this is, we have the losses, right? 2. This is simply R2 prime, IA2 prime squared. This is just the power because it's got loss in the R2 prime resistor. So after this loss, we got something called the air gap power, right? PG. This is our air gap power. So PG, this equals to PD minus the power loss. This is minus 3 R2 prime S IA2 prime square. Okay. All right. So this is just so this equation comes from just subtracting PD with PCU2. You got this equation. Okay. So there's an interesting relationship between developed power and air gap power. So you look at the two equations. They basically only differ by 1 minus S. The only difference between the two is this 1 minus S term. So it's often useful to think about this as PD by 1 minus S. This is sort of often a useful way to think about it. The amount of power you lose is depending on how big the slip is. So the slip is negative, so the larger the negative slip, the more power you lost. But then again, you need a larger slip to generate more power. So sometimes all these are related. So these are related. So that's the equation, good thing to know. And then another useful fact is to think of this is thus developed torque times the synchronous frequency. Also, if you look at the equation, that's the way it works out. So you can, in terms of torque, what you can think of as you have the same torque going through the system. And just now, once it gets to the primary side, is spinning slower at a synchronous frequency. Okay, so that's why it's useful to think about also in terms of torque, as you have some torque that's coming out of the gearbox. At the secondary side, it's going at a slightly faster frequency. Once it goes through the air gap, then it will spin at synchronous frequency, so your power goes down because you have reduced the amount of the rotation speed. Okay, so that's another way to think about PG. So that's why air gap power is a useful number to think about. This sort of is directly related to the developed power, directly related to the torque, to the slip, the frequency. Okay, so then after this is just PCU1. So 3R1 IA1 squared. This is alpha power now. This is PG minus IA minus PCU1. Okay, so we don't have a very nice equation here, so it's just subtract the two. So if you want to think about this again as voltage and current, you get this as 3 times the primary side voltage, the grid voltage, times the current that's coming in times cosine of the angle difference between. So these are all the equations we have. Any questions about this equation?
I've got a question.
Yeah.
I think usually we think about generated power as negative. Why do we think about developed power as positive instead?
Right. So the question is, right, how does sign work, right? Sometimes we want to think of generated power as negative. Why do we here turn the sign around? The main reason we want PD and PG, all this to be positive, is because when you talk about losses, and we really want to write the power, right? We really want to write PG as PD minus the loss. Okay, that's the way we want to write it. But if we have a sign convention that makes generated power negative, then we actually need to add the loss at each step. Okay, so you think of generated power as a negative number. So after the gearbox, you get a very negative number. So you add some resistive loss to get a smaller negative number, meaning that at the output, you have less power being generated. You can do it that way, but that just makes things, it's very easy to make mistakes that way because it's more intuitive. Think of subtracting losses from generated power. So it'd be easier to turn the sign around and think of the generated power as being positive and subtract off the loss. Okay? Yeah, go ahead.
In the equation, whenever you have the current square, is that always the magnitude of the complex square?
Yes. So the current square, you're right. So that's a good point to emphasize. Anytime you see IA here, that's a magnitude. Okay, that's a magnitude. Especially when you see IA square, we're squaring the magnitude. We're not squaring a complex number. Okay, it's a magnitude square. Because PD has to come out as a real number. It has to be a real number. So, right, so something to check here is everything here is talking about active power. Everything should just have real numbers, should just have real parts, should be no imaginary part, right? If you somehow get an imaginary part out of this, then yeah, you probably directly score the complex number instead of scoring the magnitude.
I have a question. What is the equation for the P gear for gearbox? The losses. Do we consider the P gearbox, the power for the gear?
Oh, P gearbox, right? So P gear is normally given to you, right? So P gear is comes from the fact that we have some coefficient of performance. So you capture some wind power, go through the gearbox. That's P gear is normally given for us. So it's not a part of the electrical system. Okay, P gear comes out of the mechanical gearbox. So we don't have a current or voltage, or we don't have an equation like that. Other questions? Yeah, go ahead.
So previously you talked about generator efficiency. Is that outside the gearbox, or does that also include like the reactive power?
Right, so yeah, so previous I talked about generator efficiency. So here we're gonna capture it as the P rotation. So the first thing that's got lost after P gear. We're not talking about reactive power yet. So here, this is a complete flow of active power. Reactive power is whatever it is, because the reason we don't talk about reactive power here is we have no control. Right? All we can do is put a negative resistor in the system. And then that just has nothing to do with reactive power. We can't get reactive power out of it. So reactive power for this kind of calculation, just it is what it is. We have no control. Okay. So the power factor of this generator will not be great. This is not a great power factor. Power factor is normally in the 0.4 range, right? So it's very far away from unity power factor, but that's not something we can deal with yet.
So in this case, we don't have excitation system in this type of turbine, right?
Yeah, we don't have excitation. Here we don't have yet. Yeah, we don't have that yet.
Okay.
There's no excitation, so there's nothing we can control for reactive power.
I've got a question on the developed torque. When I might be misremembering, but I thought when an induction machine was spinning at synchronous frequency, the developed torque, or like the torque would be 0. So if it's spinning at the synchronous speed, is the power 0? Because then the slip is 0, right? So I guess I don't really understand why the developed torque is related to the frequency like omega-2 instead of like maybe the difference between omega, because synchronous frequency is 0 torque.
Okay, so this is a good question. The question is, right, so if you talk about, let's say, induction machine being a load, then the developed torque depends on the slip, right? So normally we think of if the slip as 0, then there should be no torque being developed, right? If we think of this as a load. The point here is we have a generator, and for the generator, what happens is there'll always be a torque, because if wind is blowing, there will be a torque generated in the gearbox, right? We're generating a torque. If you disconnect the turbine, there's still a torque being generated. There's still some torque. So here, the developed torque is best to think of that's coming out of the gearbox. That's happening because wind is blowing, wind is spinning the turbine. The slip governs the transfer of the torque. Right? You can think of slips or governs the transfer of that rather than the torque itself.
Okay, cool, thanks.
Okay, so there's some torque. There's some torque here. Right? So it's not a load, right? So again, all the induction generator is not a very nice generator. Always is because it's not a load. Right? It has to do something. There's power. You have to get rid of the power somehow. Okay. So those are the equations all being typed out here. Again, this is a very important slide to know where to find it. In the midterm, you'll be looking at this slide quite a bit. There's always a question. Right, so a typical question will go something like, given the air gap power and the slip, find the developed power or find the developed torque, this kind of thing. Okay, so you have, so there's given sort of one of those numbers, find the other number. That's how these questions go. Right, again, when you see this kind of question, look at these equations, right, take your time and figure out what they are. Especially pay attention to the sign, pay attention to where the negative minus sign goes, and pay attention to that you're not squaring a complex number. Okay, you're squaring the current magnitude, not the complex current. Okay, so every year somebody will write down the developed power as a complex number, right? As it happens every year. I don't do that. So, okay, so all this, if you look at active power balance, then the shunt doesn't matter. It never enters into the picture for active power transfer. But what matters is it's good to talk about reduced mode model for the stator, because what this shunt does, what this XM does, is it makes your current computations complicated. Because you have to look at the current divider at this point. So your IA will be different from IA1 will be different from IA2, and that's a sort of bad calculation, right? So that's not a simple calculation to do if you have a current divider. So there's an easy way, right? There's an easy way to make this sort of system easier from the stator side, from the primary side, and that is simply putting this up to a Thevenin equivalent. So if you look into the primary side, what do you see? You see VA1. Okay, so we're looking into this side. So this is XM, X1, R1, and VA1. Okay, so and doing a Thevenin equivalent reduction because the voltage VA1 is again always constant. That's a grid voltage. We're assuming that voltage is not going to change. So we can have a Thevenin equivalent circuit. RTH, XTH, and then that's the same circuit. Okay. Looking into it will be exactly electrically equivalent. And then doing a Thevenin equivalent, this is just the standard equations. So the impedance, you compute these two impedances, they're in parallel. So here we have JXM, R1 plus JX1. R1 plus JX1 plus JXM. Divide this thing, you have some equivalent RTH, XTH. Okay. Then the voltage, again, this is a, okay, so this is just a voltage divider again, right? So this is just JXM, VA1 divided by R1 plus J. Okay, this is our voltage divider. This is VTH. Okay, right? So this is the way to do a sum of the equivalent circuit. So you can pretend that this shunt doesn't exist. And then in that case, IA1 will be equal to IA2. So that's the main reason for using sum of the equivalent, is to make the current from both sides equal. Any questions about the sum of the equivalent circuit? Okay, so again, just remember these equations, right? So this is again not something you want to derive in real time. Right? So after this, sum of the equivalent, then if you look at the equivalent circuit, things will be quite simple. This equivalent circuit things are very simple. Because now you can combine the R's and X's. Right? You can combine this R's and X's. So here it becomes R equivalent, X equivalent, VTH, VD. Okay, so we have a developed, right? We have a developed voltage, and then the circuit adjusts some resistance and some inductance to prime. Okay. And IA2 prime, so all these equations now becomes pretty easy to write down. Okay, so this is again the complex current, right? Complex current. VD is minus RD times IA2 prime. This is S1 minus S IA2 prime. Okay, so this is how the voltage and the current are related to each other. Okay. So what allows us to do is to eliminate IA2 prime from these two equations, right? Directly write everything in terms of VTH and S. So that's the goal. The goal is to, right? So in the circuit, what do you know? You normally know what the Thevenin equivalent voltage is. That's something you can compute. You know what the slip is. So you want to write down the current as a function of the Thevenin equivalent voltage and the slip. So the way we do it is take these two equations, right? Substitute VD, right? Substitute VD in these two equations. And then IA2 prime, as expected, becomes minus VTH RTH plus R2 prime S plus JXEQ. So this is our current we have in the system. And then the magnitude of the current is the magnitude of this complex number, VTH. Okay, so this is the magnitude of the Thevenin equivalent work voltage over RTH plus RT prime over S squared plus XEQ squared. Okay, right? So this is the current computation we have. And normally this current computation is something you do first. After you figure out S, you figure out the current, and all the power can be computed through this current. Everything can be computed here. All right, either through the complex current or through the magnitude of the current. Questions about this? Okay, so again, these equations are from basic circuit analysis. but they can be long, right? Sometimes this equation comes a little bit long. Again, just remember where to find them, and when you do calculations, be careful. Be careful with calculations. There's a lot of x1, x2, x equivalent, right? R1, R2 prime, RTH, all these things going on. Right? So be careful with this. Right? Let's be careful with this equation. Okay, so this is our current calculation, right? After equivalent circuit. So once you know the current, right? Once you get to the current, then everything here in this, all these equations can be computed, right? Because they depend on the slip and they depend on the current. So once you figure out current, you can figure out all these numbers how relate to each other. All right, so okay, so these are our equations. Right, so next we want to also be useful to compute the torque. Right, so also be useful to look at the torque. So do we want to do that now? So actually, yeah. So actually, let's take a break. Then when we will look at the torque differences, we'll draw some pictures to show sort of how do you generate the max power, the maximum torque, what are the steps that will generate, right? So for all these equations given us, and you have something coming out. So next we'll look at if you vary S, if you change S, what does everything look like? Okay, all right. So again, so let's take a break. Let's break until 9:25. Then we'll resume by looking at the torque. All right, let's get started again. So we look at the speed torque characteristics of the turbine. Basically, how does S relate to the torque, the developed torque? So I want to take something back I said earlier in class. Right? Earlier in class, I said the torque is non-zero because even when S is 0. So actually, that's not right. So in this, what I should say is the torque will be 0 when S is 0. And here we're going to do the calculation to see it. Okay, so developed torque works the same way. As you need some slip to generate some developed torque. Okay, so let's see how that works. Okay, so if we write out, so we can see this by writing out an equation for torque. Okay, writing out some equation for torque. So this is -3 R2 prime S1 minus S IA2 prime squared. Okay. So this is developed torque by definition. We define torque this way. So if you write this thing out, then torque so becomes -3 R2 prime S omega 2 1 minus S IA2 prime squared. So it's easier to use the following equation. So it's easier, we can use omega S as omega 2 1 minus S. Okay, right, this is again by definition, right, by definition of S. So here we can write it as -3 R2 prime S omega S IA2 prime squared. All right, so this is, then you can combine all these equations, -3 R2 prime S omega S VTH squared over RTH plus R2 prime S squared plus X equivalent squared. Okay. And the most interesting thing to look at is the dependence of torque on S, right? So that was a mistake I made, and the intuition was correct. Now this torque should go to 0 when S go to 0, right? When your speed is the same as the synchronous speed. Okay. So to see this equation is actually not trivial to see it, because you have S sitting on the denominator of two things, right? So you have S, for example, sitting here, and you have S sitting here. So if you look at the first term, you look at R2 prime over S term. When S gets small, that term seems to be going to infinity, right? It's blowing up on you. Okay. But then you have another S in the second term in the denominator. So what happens when S gets very close to 0? Right? Does this thing blow up, stay constant, or go to 0? Okay. On the bottom, right? So the second term goes to 0, the first term blows up. So who wins in this? Okay. Right, so the second term will win, right? Because the second term has a 1 over S squared at the bottom. So it's going to 0 at the rate of S squared. The first term has 1 over S. So that thing is only blowing up at the order of 1 over S. Okay, so the S squared wins and goes to 0. Okay, right, because you have S squared. Right? So this, when S is small, this is roughly a 1 over S term times the 1 over S squared term. Okay, so when S is small, you can ignore every other term there. That's the only thing left. So this is roughly approximately S. So this thing goes to 0. So S is small. Okay, so the second term will win. The 1 over S squared wins at the end of the day. So then let's look at the curve, look at the plot. What does this curve look like? Well, so let's write this as speed. Okay. So this is the synchronous speed, right? So let's plot this term as torque. So this at omega s, this means a slip at 0. We have 0, right? We have 0, right? So as this, when s is 0, you have 0 torque. When s is slightly larger than 0, this thing starts to increase. This thing starts to grow, and will look something like this. If you plot this, it will look something like this. Okay. So what we have here is we'll have a maximum torque, right? So this is called the pull out torque. This is the maximum torque you can get out of this. So this is pull out. Okay. Right. So this is the sort of this is called a speed torque characteristic. The speed torque characteristic. All right. So again, when you operate the turbine, you want to make sure you have your speed is above the synchronous speed. Otherwise, you have power going into the turbine, right, which is not very good. You want to make sure it's the speed is higher than the synchronous speed. You want to make sure your speed is lower than the pull out speed. Because once you get to the pull out torque, then things become unstable. Okay? Things become unstable. So your operating region is actually quite narrow. You want to operate at this region. Okay? You want to be above synchronous speed, but not too close to the pull out torque, okay? For stability reasons. Any questions? Okay, so this is the speed torque characteristics. Again, this the equation for torque. It looks complicated. Again, comes from sort of combining more basic equations together. Right, so that's for torque. So it'll be interesting to compute. So what is the maximum torque you can get? Right, that's an interesting number to compute. That will also give us an idea as what sort of your maximum slip is. Right? How large your slip can be. So let's look at that. Let's do that computation. So this is speed torque characteristics. So we do that computation again. The torque is this minus. So the dev power over the frequency. This is minus 3 R2 prime VTH squared S omega S RTH S. Okay. To find the maximum, right? Let's take a derivative with respect to slip and set it to 0. So that's how we will maximize this. Okay, so after you do this derivative and set it to 0, will turn out there's not much point on computing this, but on showing the calculation. So the number comes out this way, okay? The R2 prime over square root of R1 squared plus XQ squared. This is where the maximum slip occurs at. When you maximize this equation, that's where just the number that comes out. And then the torque, the maximum torque or the pull-out torque, you substitute this thing back in. This is 3V squared, 3VTH squared, 2 omega S R1 plus R1 squared plus X equivalent squared. Sorry. 2 omega S R1 plus 1 squared plus X equivalent. Okay, so that's just what the equation comes out to be, right? So if you do a 7 equivalent reduction, then this is the maximum torque you can get out of the system, okay? And this maximum torque depends on the voltage, depends on the R1 parameter, the X equivalent parameter. Okay? So why doesn't my maximum torque depend on R2 prime? Right, so you look at the maximum torque, this expression, this equation, R2 prime is somehow not in this equation. What happened to R2 prime? Why is the mass torque just independent of R2 prime? So intuitive, right? So if you can do the calculation, this is sort of the number that comes out. But again, intuitively, why? Why is R2 prime not showing up in this max torque equation? Okay.
That would be the rotor, like it's torque between the springs and the aircraft.
Right, so yeah, so in class, one way to think about it is the torque, right? So on the rotor side, the rotor is part of the torque, so you're maximizing the rotor side. Then what the torque is left over is between the air gap and the as in the air gap. That's one way to think of it. But actually, the equivalent reactance show up. So X2 shows up in part of XEQ. R2 never shows up. Right? So the reason R2 prime doesn't show up is you remember to the circuit we have. R2 prime shows up as R2 prime over S. Okay, that's where S appears in the circuit. So maximizing over S is the same as maximizing over R2 prime over S. And they show up as the same variable. So maximizing one means maximizing the other, right? They only show up together in one part. Okay. So after you maximize over S, as if you maximize over the term R2 prime over S, and R2 prime doesn't show up. Because if R2 prime showed up, then I can change S to make R2 prime over S look something different, right? So that's why R2 prime isn't there in the final torque equation, right? In the final, in the maximum torque equation. Okay? So the maximum torque depends on right? So given the setup of the connection to the grid and the reactance, there is a maximum torque you can develop, right? You can deliver. So again, there's not the more wind blows, the more torque you can get. Right? There's a max given the generator type. So, right? So if you have more wind than this, then again you have some problem. Okay, so this is the maximum torque we have. All right, so let's do some calculations with all these equations. Right? So let's do the calculation and see all this equation and current coming into play. Okay? So let's say we have a type 1 wind turbine, 6-pole, 60 Hz, 3-phase, Y connected, spinning at 1250 RPM. So this is just very standard turbine. Okay, so yeah, so I guess one interesting thing is for 60 Hz, so the gearbox for wind turbines are actually slightly different because we have 60 Hz grid, Europe has 50 Hz grid. So that will matter when you're actually making a wind turbine. Where are solid 2, the frequency matters. Okay? But for our calculations, it will always be 60 Hz wind turbines. Okay? The terminal voltage of the generator is 690 volts. Bunch of parameters, right? So X, R1, R2 prime, X1, X2 prime, XM. So we're going to ignore the core losses, right? So there's no RM, there's no RM, there's no resistor on the core on the shunt. So we're going to ignore that part. We ignore the rotational loss, so we're not going to worry about the generator not being efficient. Compute a bunch of things. Okay? Compute the current, compute the developed power, compute the air gap power, compute the final power we deliver to the grid. So for this problem, right? For this problem, if you see XM and the problem doesn't say ignore XM, then you have to use a Thevenin equivalent circuit. Okay, so we're going to do this in class to see it once. Right? In homeworks, often or in exams, you always see a question say ignore XM. Or if XM is not given, ignore it. So in the homework, in some questions, some parameters are not explicitly given. For those, just assume they're 0. Okay, just assume they're 0. Right? So we'll do this example in class because it has everything in it, has all the parameters in it. Okay, so we'll do a Thevenin equivalent calculation as well. Okay, in exams, we typically do not ask you to do the Thevenin equivalent calculation. Okay, so that's not a very important part. But here we're going to do it. Right? So let's do a Thevenin calculation first. After that, we'll find the current. After finding the current, we'll find all the power. Okay. So a Thevenin equivalent calculation, let's compute the Thevenin equivalent voltage for this. Okay. This is JXM, a voltage divider, R1 plus JX1 plus JXM. Okay. All right, so again, the most common mistake people make is this is 690 over √3. Right? There's a line-to-line voltage that we're given. So you need to divide by √3. The grid always has angle 0 for us. Okay, so the grid always has angle 0. Right, so the natural reference for angle is a grid angle. So this is what are the numbers? 10 milliohms, 100 milliohms, and 2 ohms. Okay, so this is 0.01 plus J point 2.1. So the sum of the equivalent voltage is 79 angle 0.27 volts. Okay, so just what you get by putting all these numbers into it. Right, and the thing to remember again is the grid voltage VA1 has angle 0. That's what we're going to refer to as angle 0. The Thevenin equivalent voltage in general is some complex voltage. We'll have some complex angle. Okay. So that's will not be very different than the grid voltage, right? The angle is typically small. But anyways, we'll have some non-zero angle. The sum of the equivalent impedance, parallel impedance. Putting in all the numbers, we got 0.009 plus J 0.095 ohms. Okay, so this is our sum equivalent numbers. Okay. Right, so after doing sum equivalent computation, we'll find the slip, right? So that will give us a current. So the slip is okay, yeah. So the part is from the current. So slip here is an S minus N over NS. So if you look at N, that's 1250. The synchronous frequency will be 1200 RPM, right? So there's only a few synchronous frequency out there, right? So you can do the frequency over the number of pulse calculations, but often if you look at a number like 1250, then the synchronous frequency will be 1200, right? Because synchronous frequency goes 3600, 1800, 1200, 900. You're dividing by even integers. So this is 1200, 1250. Slip of minus 0.0417. Okay. All right. So and then we look at our IA equation. Right. So what happened to our IA equation? We have this equation here. Right. Just apply this equation here. Okay. So applying equations, this becomes minus VTH. RTH plus R2 prime over S XTH plus X2 prime. Again, not writing the numbers, 125, angle 40.23 kiloamps. Okay. All right, so that's just the current flowing through the rotor. So the problem says occurring in the rotor circuit. This means compute IA2 prime. Compute this number. So we have computed this number. Now let's compute the developed power. So again, this is again knowing what equation to use. Plugging that equation for developed power. Okay, so let's compute that. Well, developed power, if you look at the equation we had before, this minus 3 is to 1 minus S, IA prime squared, right? This is our developed power. Putting in all the numbers, we got 18 megawatts. Okay. Okay. So here again, the important thing is to square the magnitude part, not the whole complex number. Okay. To square the magnitude part here, so you get 1 megawatts. Then the air gap power is a developed power, subtract on the power loss, PCU2. This is PD minus 3 R2 prime, IA prime squared. You get 1.132 megawatts. Okay. Okay. So again, the important thing to remember is there is a 3 in all of this power calculation. There's 3 times the current times the resistance, right? Because we're talking about 3-phase circuits. Okay. So that's why the question says, we have a 3-phase Y connection induction check. So that says, right, so all the 3s are to show up here, right? So don't forget the 3. Then part D, so this is the next we find air gap power. We found next we want to find power delivered to the grid. Okay, one time power delivered to the grid. So to find power delivered to the grid, this can be slightly tricky. So part D is a slightly tricky part. The reason part D is slightly tricky is now we can't, we have to go back to the original circuit. We can't just use the Thevenin equivalent anymore. Okay. Because what we computed was IA2 prime flowing this way. Right? But to compute the power to the grid, you need to compute the loss on this R1 resistor. Okay? We need to compute this loss. But then, so we need to compute IA1 prime. Okay? So this requires us to actually can think about this XN. So that's where the tricky part of this question is. Right? So everything else we can do using Thevenin equivalent, but here you have to deal with this current divider. Okay? You have to deal with this. You have to deal with current. All right. So that's the question we have here. So the way we're going to deal with it is to let's first find the VM. Okay, we're going to find the voltage across this shunt branch. We're going to find the voltage across the shunt branch. So we're going to find the VM here. And then the way we're going to compute IA is we'll compute IA as VM, subtract VA1, R plus JX1. Okay, so this is our strategy of finding IA1, compute the voltage, and compute the current. So let's see how we can compute this voltage. Okay, let's see how we can compute this voltage. To compute this voltage, what we have is we have Kirchhoff's voltage law. Right? This voltage drop must be equal to the voltage you get by the current going through the rest, right? By the current going through the right part of the circuit. Right? So that voltage drop is 0. Okay, so you look at VM. What is VM equal to? Well, VM is equal to negative IA2 prime times R2 prime S plus JX2 prime. Okay. So this is the only tricky part. This comes from adopting Kirchhoff's current law in this circuit. Okay. So the voltage drop. Okay. So we have a voltage on the, we have a current IA2 going through R2 prime over S plus JX1. Okay. That voltage must equal to the voltage drop on VM. Okay, so that's Kirchhoff's current law. Kirchhoff's voltage law being adopted there. So we can compute VM. We know IA2. We can compute VM. Through this equation, we got this as 326 angle 17.6 degrees voltage. Okay. And compute VM this way. Then IA1, using this equation, plugging everything in, we got this as 1.31 angle 47.3 degrees kiloamps. And then the power output is the air gap power minus 3 R1 IA1 squared. And this becomes 1.085 megawatts. Okay. All right, any questions? Okay, so was the right. So everything else in this was, very straightforward. The only relatively tricky part was this VM computation. So this is a good equation to remember and know where to find. Good. Yeah. No, VD is not 0. So let me do that more clearly. So you look at this circuit, right? On the right hand side, this is X2 prime. This is R2 prime, right? I drew this as VD. But VD is really minus R2 prime S, 1 minus S. Right? I can add this as a resistor back into it. So this is equivalent to some resistance with developed resistance R2 prime S 1 minus S. So that's why we get this equation here. Okay, so this is the part D is the part testing that, once you convert something equivalent, can you convert it back? And can you look at this current divider? Any other questions for this example? Okay, so this is where sort of, this every other part of this question is look at which equation to apply to. Sometimes you have this sort of part versus not obvious, but then just remember sort of circuit theory. Right? All this part is basic circuit theory. There's not, there's not much deeper things going on here. But knowing where to find this example is useful, at least for doing homework. Doing homework, you'll see something like this. In exams, often the problem will be more simplified. All right, so this is sort of all the calculations basically you can do for type 1 turbine. Again, it's just an induction machine. Right? Everything we can do is in a question like this. Okay? So now it's time to look at sort of limitations for type 1. Right? Type 1 was not a very successful, was not super successful. It was not super successful. So there's a lot of drawbacks around it. Right? And these sorts, we're going to try to fix the drawbacks. So the number one drawback for type 1 turbines is again that we need a synchronous frequency. Okay, so this type 1 must be connected to the grid. Okay, because we need something to set a synchronous frequency. This will not operate without synchronous frequency. So this cannot be a standalone type. Okay, this cannot be a standalone system. Right, so that's why when wind turbine was first developed as for providing people who's far from the grid. So this is obviously not a very good strategy, providing people who's far from the grid. Right, you want to be more standalone. So type 2, this is reactive power. It cannot produce reactive power, actually it must consume reactive power. So this causes a lot of voltage problems. Okay, so for folks who, for example, who's taking distribution system or have seen through reactive power and voltage, as normally, the more reactive power you consume, the lower the voltage is. So it's hard to maintain a good voltage. Right? So this type 1 tends to drag down the voltage of the entire grid. Right. So there is another actually limitation that's not as obvious as these two. But that was also a big problem when type 1 was first put into production. Think of another limitation. It's a little bit unexpected. People figure it out after putting this here. Okay, so what happens when you're trying to start, when you connect let's say a generator for an induction machine that's not spinning, right? That's a zero frequency. When you connect that to the grid, what happens? Right, so the machine now has to catch up to the grid, right? Very quickly catch up to the grid. But then what happens when the machine very quickly tries to catch up to the grid? Okay. Right, so your S value is very large. Right? You have slip of 1, basically. Right, you have slip of 1 because your frequency is 0. What happens when slip is 1 is you pull a lot of current through the grid because you're trying to catch up, right? You're not doing anything. You try to spin up, so there's pulls a lot of current through the grid. So when the machine is starting, there's a very high current at starting. Right? And the machine is idle for a lot of time, right? Because type 1 can only operate, in a very narrow operating range. So often as the wind gets too high or too low, you lock the machine. But then you have to restart it, then pulls a lot of current from the grid. So why is pulling a lot of current from the grid bad? So what tends to happen if you pull a lot of current from the grid? So what in the grid senses high current? Right, so we have an inrush current that's very large. So what happens when you have an inrush current that's very large? So how do circuit breakers work? Right, senses current and trips protection. So this tends to not only trip its own protection, but trip other people's protection. Because you're pulling current has come from somewhere. So then, some protection device may think I have a short in the grid, right? So I have a short circuit fault, and that's not great for this, right? So this trips a lot of protection. Okay, so we have come a long way from these type 1 machines, right? This was really a proof of concept at that time, as you cannot put a lot of them in the system. Good. Yeah. Yeah.
You can't create this line power from a different right? You still need a reference.
Right, you need a reference that's fairly constant.
Yeah, it can't just be another.
Yeah, can be another winter run. I think it's also changing. So it's not a reference. You guys are sort of fighting each other. Right? So you need some constant reference, right, for the first one. So this was first thing again. Was small number of them, right? So the current, at least you don't trip other people's protection. You don't mess up the grid voltage, and the grid is very big compared to you. Okay, so induction machines are easy to make, but has a lot of this kind of problem, not very controlled. Right? So there's a lot of limitations. Right? So again, in 40 years, we dealt with most of them. Right? Nowadays, we don't have these limitations, right? So, but the field, the big part of the struggle was to deal with these. And these are not obvious ones to deal with, especially this protection issue. Right? So you want to protect against short circuit faults. But then how do you know it's a wind turbine turning on versus it's an actual short circuit? And we're starting to see this again in today's grid. As for example, we have a lot of renewables. A lot of them tend to have current surges. So a lot of them, when you first come on, they tend to have current surges all the time. And then protections are not having a good time with current surges. Right. Okay. So we solve them for wind turbines, but there's other devices that has these kind of challenges. Okay? Right. So the reactive power is perhaps the easiest thing to look at. Right. So reactive power again, because reactive power, all of these are inductors. So there's no capacitive element anywhere in this circuit. So with reactive power, if you draw the plot of again the speed and the reactive power, then at the synchronous speed, nothing happens, right? Nothing happens. But then above the synchronous speed is always positive. The reactive power is always positive. It's not, something has to provide reactive power to the system, right? Because, so you want to compute all this, right? Again, this is not very difficult computation. IA1 squared, Q2 is 3x2 prime IA2 squared prime squared. QM is 3xm IM squared. Okay. Right, so your total reactive power is the sum of all these. So sum of squares, and it's always positive. There's nothing you can do about this. Okay. So reactive power being always positive, so that means that the active power is coming out of the generator, reactive power is going into the generator. And there's another reason it cannot be a standalone system. And something has to provide this reactive power. Right, so And then we can look at inrush current. Right, so inrush current means when you, at the moment you connect to the grid, your speed is probably very different than the synchronous speed. You have a relatively large slip. Then you have a large current. You have a large current going through the system, and it's called inrush current. So often the design of the machines are limited by the inrush current it can handle. This is the design limitation we have. Okay. So let's do an example to see sort of how large these currents are. So this is the exact same setup as before. All these numbers are exactly the same as the example we just have seen. So we're assuming what happens is, this turbine is spinning faster, right? So before it has a rotation rate of 1250. Now let's say it's spinning at 1350 rotations per minute. Let's say just spinning faster, then it gets connected to the grid. Okay. Let's say spinning, gets connected to the grid. Let's see what happens to the current. Okay. So as a comparison, at normal operation, what we computed before. Right, so this is 1250 RPM, a smaller slip. IA2 prime was not a vector, not a complex number. IA2 prime was 1.562 kiloamps. So this is sort of the normal current you expect. So here, let's see what happens as well. If once you first connect it, has a much larger slip. Has a much larger slip. So this is just the same calculation again with a larger slip. Putting everything here, we got 3.447 kiloamps. Okay. So the ratio is some 200% increase in current. Okay, and your protection devices do not like this kind of dynamic range for your current. Right. This at some point this will start look like a short circuit fault, but then it's just a normal connection to the grid. Okay, and large current again damages equipment, trips protection. So there's a lot of challenges. We have a very large inrush current. Right. Okay. So can you think of a way to reduce this? Right. Good. Yeah. Right. Yeah, so we can do it that way, but that's also a little bit challenging. Your slip changes all the time, right? You don't know when you connect. Any other ideas of how to reduce this? So back to power electronics. We're going to cover more power electronics later on, but think of power electronics. Right. So changing the blade and the slip, that's harder. That's a mechanical system, takes a long time to do that. It's way easier to just install some power electronics and deal with the other way. So what people came up with is basically the one way you can do reduction is, let's say you have a grid. Right? Let's say you have a grid here. And then one thing that makes this current large is this summoning equivalent voltage. Okay, the summoning equivalent voltage sits on top of this equation. So if somehow I can reduce that summoning equivalent voltage, I can maybe make the a current appear smaller by making the grid appear to have a lower voltage to reduce the current through my system. So the summoning equivalent to reduce the grid voltage. So I'm going to draw a single phase equivalent and not draw 3 phase. But so think back to 351 or the power class you took. What is a good thing to put in here to reduce, give me control of the voltage? IC. So buck converter is for DC circuit, right? So for AC circuit, what's the equivalent of buck, right? What's the equivalent of buck converter? Not a transformer. I want something that's controllable, so not a transformer. Anybody remember? So what is the AC to AC voltage converter that's sort of controllable in 351? I've spent a lot. Which one of these has long equations with there's alphas and sines and all that? SCR, right? So your girlfriend from that class comes back, this ICR. Right, so what you do is, okay, you have a, right, so you want to control the voltage. So what do? Well, first you have a switch. So this switch only closes when you're ready to connect, right? But then you have your SCR back to back. Okay, so this is the way you control the grid. And by changing the triggering angle, I can make the voltage from the grid appear smaller than it needs to be. Right? And the triggering angle is again something I can adjust. I can adjust the triggering angle, so I can slowly let in more voltage from the grid. Okay. So CR again is in some sense developed for this kind of things. It's a bulky equipment, bulky device that can tolerate a lot of voltage and current. Okay, so that's why we use bipolar transistor for these, right? These are very first generation electronics, and they're there to regulate voltage. Okay, so this will become more important, but this is just a crude application of SCR. Right, so for you guys to right, so the grid voltage, this VA1. Well, the VA1 voltage looks something like this. So just to remind you, this kind of equations, we'll look at a lot more of this kind of equations later. Right, so that's the ICR equation you saw many times in 351. So this is the idea of reducing voltage, dynamically controlling voltage. This idea actually comes back again and again in winter. A lot of times you have to deal with current and voltage issues. So SCR are quite useful. Just a reminder of what happens here. Okay. So that's one issue. Then stability. So last thing we're gonna look at this class is look at stability. And think about what happens in stability. So right, so here we have mechanical power into it. We're gonna ignore losses, right? So after some losses, mechanical power into it, and then if your mechanical power is larger than the power can get out of the turbine, right? You can get power out of the generator, then you really has a problem with this. Because what happens is then the energy in your mechanical power is larger than the energy output. It's really a buildup of energy. Okay? You're really building up this energy. Building up this energy is not very good. Okay, you don't want to build up this energy because at the end of the day, again, this energy has to go somewhere. This energy has to, this conserved has to go somewhere. So in this system, where does this energy go? So let's say you just have a lot more power from wind that you can deliver to the grid. Starts to build up. But physically, what happens? So what will you observe if you have an energy imbalance? Yeah. Right, things will blow up, but what exactly blows up in this room? Right, so gearbox. Right, but the answer is everything that can possibly rotate will start to rotate fast. Right, because you have this energy, the energy has to go somewhere. It can't go to the grid, it can go back to the wind. So it has to get converted to rotational energy. Right, there's a lot of spinning parts. All the spinning parts that can spin will spin fast. And that's where the energy has to go, right? So everything speeds up. Right? So your gearbox spins faster, your generator spins faster, everything that can spin will get more energy to spin faster. Then so eventually, right, this, there's a limit how fast you can spin, and things blow up. And then you see parts fly around. Okay? You have all this angular momentum that's gonna build up, and things just blows up on us. Okay? So go to YouTube, search for this. Again, you haven't looked at it, you should take a look. It's quite fun. Okay. Right.
Is this basically where you go over that maximum?
Yeah, that's as we get close to that. Yeah, we go. Yeah. So there's nothing. Once this happens, there's not much you can do. Right? Your goal is to stay far away from this one. You don't really want to think about what happens when you get to this point. Okay, so stability is a big problem for this turbine. So how do you deal with stability? Right, that's basically the idea. It's a huge problem for this kind of turbines. How do you deal with it? Right? You don't want things to blow up. So there's two options. There's two options to restore balancing of energy. Okay, right? So the first option is just reduce mechanical power. So reduce the power that's coming into the system. Right, so this is doing, for example, pitching the blade, right? So the main thing you can do here is pitch the blade. Right, trying to pitch the blade to sort of reduce the amount of power, right? To reduce CP, basically, so they don't get that much power into it. Right? But what's the challenge with this, reducing mechanical power? So imagine the scale of the wind turbine we show, right? That's sort of 100-meter long things, right? You cannot pitch the blade that fast. It will take you some time to change the shapes and pitch of this large machine, right? Large component. Okay, so this is slow. Slow meaning on the order of few seconds. Okay, right? It's just slow. It just takes some time. There's a lot of inertia in the system, so they're big. Take some time to pitch the blades. Right? Your system may not survive. Right? Your system may not survive this few seconds, actually, depending on how much power you're putting into it. But what's another option? So if you give me a few seconds, I can pitch the blade. I can probably reduce mechanical power into it. But how do you survive this few seconds? Right, switching a battery system. Right? It's actually, right, again, this seems not very sophisticated, but this is what we do. So increase the load, right? Increase electric load. This is right. So again, you don't have to just increase the load all the time. There's a way to rise through the time you need to pitch the blades. Right? So you have this sort of failover device. So most times this is so increasing the power. This basically says dissipate this in some circuit. So dissipate into some external circuits. If the grid doesn't want it, then we have to dissipate this in some resistor. Okay. So basically, you get this kind of system. This is called a stator dynamic resistance. And what this does is basically saying, I have some rotor. Okay, so normally, if I close the switch, I will bypass all the resistors. So I deliver all the power to the grid. If there's some fault, right? If something happens, I open the switch. then my power will go through the three resistances, and I burn up some power that way. Okay, right? So this is a controlled way to improve stability, to get rid of power, to get rid of active power. Okay, so that's the way we do it. So we'll stop here in this class, because next class we'll compute some equations for these. You'll see that even for a very large resistance, you're probably not going to live very long. So this is really, so but you need pretty large resistances, and you can dissipate a large amount of power in a few seconds. You're limited by that you don't melt the resistor. Okay, that's basically your limitation. Okay, so this is dynamic. So the dynamic word comes from the fact that, again, we're using the SCRs in parallel with this kind of switches. Okay, so we have some control of how much power we want to dissipate. Okay. We'll stop here today. Next class, we'll do a very quick review of SCRs. Right. Again, just looking at, writing down the equations again of what happens when we have AC wave going to SCR. Then we'll finish type 1 and then go to type 2. Okay, right. So see you guys on Tuesday.